My name is Martin Janus, and you probably don't know me very well, but I have been in the BGP development area for 20 plus years, the last 12 at Juniper. So I feel very familiar with how BGP works, how BGP is deployed, the issues you might see. This talk is not technically about BGP, however, it is something very important to BGP, which Ron came up with over about almost 10 years ago. It's called a TCP authentication option. My goal here is that you come home and saying, I want to use this. But before we start this talk, I kind of would like, anybody here who's using BGP authentication in their network today? The authentication option, TCP authentication option. One. That was more than I thought, thank you. Anybody who uses TCP MD5 on any sessions? There are some, okay, that's a lot more than I thought. That is also very encouraging, so that's very nice to hear. That's good to know. Let's see if I can move. People have had problems with this. Okay, so first of all, why do we need TCP security? That seemed to be such an obvious question, but I'm still going to say something about this. I don't know how many of you who was aware of it, but back in roughly 2004, there was a reset attack on TCP. TCP sessions are long-lived at the time. Most BGP configurations are pre-configured, so IP addresses, source and destination IP, the BGP protocol number, they are all static. Right? Everybody, they're easy to guess from an attacker. So we have the TCP source port, which, okay, not that hard to get to it. After all, it's a long-lived session, so on. There's ways to get to it. And what people then did, or what attackers then did, was they started sending a slow rate of TCP resets to a spoofed network. They spoofed basically some peer's address and tried to send it slowly to the setup. And because they were using a very low rate of just TCP packages with a reset bit set, it went under the radar. And eventually, by doing random sequence numbers, the reset message would hit the TCP window that was currently valid, and poof, the session would go down. Now, TCP session going down, if it happened to be, telnet, whatever, you might not think it's bad, but because BGP protocol is reliant on this session staying up, it means that when the session goes down, we tended to take down all the routes and withdraw all the routes from the peers. Basically, there's a big churn in the network. So it would be quite catastrophic for most providers if that happened. And even though the session would come up again and after this, it was certainly a scary moment for them for that setup. We have BTSH or DTSH, as it's called nowadays, for the generalized TTL security hack. That one can prevent you from getting packages in that is coming too far away, but we see local networks get hacked. With SolarWind, for example, they have hackers have access to their local network, meaning that you cannot guarantee that nobody have hacked into your network to sit and send these messages through your network. So basically, anybody who is in your own network might be able to spoof these messages. Also, they don't really apply to IBGP in the first place because the way IBGP is designed to not do the TTL check. And while you can do a multi-peer, or you can do filtering on your peering sessions, if you have 1,000 peers, you have to remember, you have to at least make sure that none of the 999 other peers could possibly have been sending messages as well, more than, on their interfaces. Otherwise, every single one of them would be a potential attack. There's a lot of ACLs, a lot of things you need to get right to make sure things is safe. In 2004, people started then really quickly trying to deploy MD5 in their networks because it happened to be the way we quickly could get some level of security. Even back then, MD5 was known to be on the edge of going out, basically being insecure. The MD5 algorithm has been hacked in the meanwhile. It is considered not a secure hashing algorithm by today's standard. So we really need something better than that. The other thing people realized quickly was, Jesus, how do they change the password? MD5 doesn't have inherited key rollover. So changing password could work if you sat console to console and pressed enter on both sides. If you were within a couple of seconds, it probably worked. If it took longer than that, it might not. And I said probably, there was no guarantee, right? It was just happened to be possibly working or not. So that certainly was a problem. And because of this, years and years later, providers were seeing they were using the same MD5 passwords. They had people leaving the company. Technically, they know the password, and nobody have ever, changed the password because of it, or at least very rarely because, Jesus, I don't want my TCP session to go down. That's why I did this in the first place. So that was kind of the, how do we encourage this? There's also replay attacks, which is an issue. And I'll get a little more into it later, how here the TCP authentication option deal with that. But basically, that is also one of the things it helps with. I have mostly spoken about this. So I will skip over the slide as I mentioned it before when I talked. So MD5, the way the option works is it takes TCP payload, including what is called a pseudo header, so IP address and port numbers, and it calculates the hash and inserts it into the message and sends it out for every message. That and the receiver will it gets the message, and first of all, if it doesn't have a hash on it, it will, of course will discard the segment. But at the same time, it will, if it works, it will then recompute the same thing, and it will validate if the MAC is right, and if it is, it will move on. It will accept it, otherwise it will drop it. Works, as I said, but the problem here is you can't, MD5 is old, not trustworthy, and we can't change the password. So the new requirements is we need to be able to do key rollovers. We need to also, another thing we strongly believe in is that we need to be able to implement this new option, TCP authentication option, in a way that we can add any algorithm later without changing the protocol. Now, it doesn't mean that code doesn't need to be changed, because if somebody adds a new smart algorithm, you have to, of course, implement that algorithm, right? But there is no key points that need to be allocated at the IETF. There's no data in the IETF that need to be pre-formatted in a certain way in the TCP option to make this work. There is just the authentication option, and it has the ability to do so. I just need to check that, have it on. Okay. Yeah, that's basically the ideality. We need stronger ability to move on to stronger passwords as we are having now. So now, how is this implemented in TCP authentication option? So the TCP authentication option has what's called an MKT, or master key tuple. Basically, you have a master key, and it, in addition to the regular passport you will recognize, has some information like what kind of hashing algorithm is it using, what kind of parameter session does it apply to. Most I know there are multiple vendors that have implemented it this way. For example, is this valid until a certain time or in a certain time window? So you can set for example, the validity of your password to be until midnight, tomorrow night, and then it will switch after that. It will be seen as invalid after that. What it also does, what TCP authentication also do is, it uses traffic keys as opposed to the real keys. The master key is not used on a hash like it is in MD5. It's abstracted away. So it uses the primary, for almost all messages, it uses the initial sequence number to generate together with the known topology numbers, so IP, source, destination, port numbers, and so on. It will, and that sequence number, it will generate a send and a transmit key. And these keys, the send and transmit keys, are used for the actual sending of data. It also means that if somebody knows the master password, they can't recreate the actual key that's used for the session unless they know what the initial sequence number was at the time. That means that just because that you're using the same password for 2 sessions, that the 2 sessions are not using the same secure key for passing on your for ensuring your data is untampered with. Right? So that makes it way better in that also the actual key you're using, TCP session goes down and come up again. It's a new session. It's a new key that is generated for the new session always. It also uses a hold on, give me a second. So it has the following data in the actual TCP data it is sending. It's sending obviously the MAC, but it sent the key ID and it received next key ID. The key IDs is a configuration thing. You can specify any value you want, 0 to 255. There are no reserved numbers. There are no invalid numbers. You say that in, for example, Juniper or Nokia's implementation, I know they say configure ID 25 is whatever algorithm I want to use. Here are the session it belongs to, and this is being applied as transmit key for this session, and I can use a different one as a receive key if I want to. Which means that whenever you're doing that, the receiver side just looks up and saying, okay, I have my receive key from this session, and now I can check what kind of hash algorithm I'm supposed to use for it. And since the receive key is a part of the check itself, it can't be tampered with. I know it's safe to use it, and I can take it as an indication of which algorithm I'm supposed to, which master key and which active key that is used for receiving data from that session. So that means that we have the flexibility and agility to move on to these other, all of these other keys later on. There are currently at least a couple of different implementations of key, algorithms already that works really well. It also has another one. It's called a receive next key ID. The receive next is essentially the sender says it is used for rollover. First of all, so basically, the receiver says, I am now sending you a packet, and I'm expecting you to send the next key to be this value. And if the sender also has a configuration that says I'm supposed to be sending this key soon, or actually I have a valid, because you can have multiple valid sending keys. If I have a valid sending key for this, then I will move over to it and use it following for the next packet coming back, but not before. And that means that the rollover is coordinated between them, and they will both switch at the same time through the receive next ID. Okay, so the master key tuple has connection identifiers, as I said. You specify, for example, with or without wildcards, by the way. This is the IP addresses I will allow this key to be used for, so that when I put it on the system, it applies to them, even though it was misconfigured, maybe on a different session or whatever. In that case, you won't be using it. You can also do things like if the options section of TCP is included or not. That is the information. And then there are the sending and receiving key identifiers, which I talked about right before. They are used exclusively to hand over between the two sides. There is nothing in the protocol to specify what the value is supposed to be. They are coordinated completely by the two sides when they configure the routers, and are only used to identify which MKT to use for validation. There are technically 4 different keys generated for each MKT. There is a send sync and send and receive sync, and then there's send and receive other, the generic ones. The send and receive sync is going to be used when you set up the session. Send is obviously sending the first sync over for the TCP connection. There's still no ITIN. You have no initial sequence number, so you can't just say this is the sequence number. So I can't use it. It is basically set to 0 when a new key is generated. But for everything following, they will move on to the one with the send other key, send or receive other, I should say. The receive SYN is only, or these two usually are only used either one of them. It is only if we have something called, very arcane old TCP, which I don't actually think that anybody is really aware of that is supported. Simultaneous TCP open, where you get a SYN from the same TCP session at the same time. Then you can have both of these two active, but otherwise you won't see both of them. This is how the authentication option looks like, and if you have seen the RFC for MD5, it's very similar. There's a difference here, is the length value is now part of it, and obviously the key IDs are in here. Now, the length is included. First of all, both of the setups we use today are using the same key length, simply because it's considered okay from a security standpoint to use that length today, but the length is completely flexible in the spec. Any future defines on how you want to use it, can use any length you want. And key ID, as I said before. So basically, okay, we put it all together. So each node is configured with one or more MKTs, and whenever they have an MKT, they derive traffic keys from the MKT. So that means there's an abstraction that whatever master password you have in your MKT is not used for actual traffic access. The traffic keys are then used for hashing or validating your data, and validating the data. And then one more thing is that basically today, you could technically use any method you want to synchronize when you're going to switch over to another MKT. There is nothing in the spec that says anything. As I said, I know that Juniper and Nokia are using time. So basically at a certain date and point in time, I can't remember if Cisco does it too, but definitely Cisco has also an implementation for AO. But basically you can do that, or you can do any other method you want to. You can have an out of band or phone call, whatever you want. I mean, I don't advocate a phone call, but I'm just saying you could use any other protocol to do that if you felt like. Again, the procedure for TCP AO is very similar to MD5. It calculates the MAC, the message authentication code, based on the segment and the TCP properties, and it inserts it into the segment. And then from the segment on, it is sent out on the other side, and on the other side it receives. It identifies which key is used, and based on which key is used, it will then validate the packet. Okay, so here are known releases for support, which support this. Linux, this is a slightly old version of the slides, it doesn't matter. RIPE is funding the Linux implementation and is being committed as we speak. And Wireshark, also the same, is being committed as we speak. I mean, that's not RIPE, was I think some university students who wanted to do that. And is GitHub repositories, where you can find some configuration examples and so on for these, and I would definitely would, suggest you go and have a look. As well as I think you should listen to Ron and a great presentation on the Routing Table podcast. Since it wasn't me, I can definitely do that. Now, why don't we just use DTSM instead? I kind of started out by saying most of this in the beginning, so I just will do this one very quickly. Because I don't think there's anything I haven't said why it's not just enough. We have to use security in layers. We can't just assume that I have implemented, let's say, ACLs around on my network. ACLs can go wrong. You have an IP wrong. You have applied something wrong. You forgot something. You thought it was working, but it isn't. That's actually the worst thing, because suddenly somebody can come in behind your back and stab you on your back, and you didn't know. So we need more layers, and therefore, really, what I'm going to come out of this is I want to encourage you guys to deploy all of them, because we really need them. And I really think you should switch on TCP authentication option, as opposed to MD5 for sure, for all the ones that already does it. There should be no drawbacks, short of that it's still kind of not everywhere. All platforms, all versions of code, of course, doesn't have this. I'm aware of that. I know there are many providers that runs around and run, not just 2-year-old code, but even older than that. Apologize, but I'm certainly aware of that. So I'm not. If just a couple of you come home and take it up, I think that's a win. I don't want to go over this slide specifically, but basically we had done interrupt testing together with Nokia. It was done during the pandemic over the internet, and nobody had to meet in person, virtual machines, and all of that works really well. And these are the two algorithms here is the ones that have been used. The configurations you can find online as well in the repository. I do want to mention here there was firewalls. We found that there's firewalls that actually modify the MSS in the TCP, and of course, TCP AO found this and saw it to be invalid and dropped the sessions. It took a little bit of debugging to realize. So keep in mind that can be. Questions?
Are there any questions?
Hello, Matthias from Cisco.
Welcome.
If no one else will ask a question, I will. For this, you talk about there's a lot of flexibility in terms of which authentication algorithm you can use, and multiple ones exist. Can you just elaborate which ones already are implemented and work well, or just, I presume, is it on the GitHub, or where can I find that?
No, that is, so I don't remember the FC number. This 1+1 has actually listed the ones that are currently recommended to be, implemented. At SHA-196 and EAS 128 CMAC has been implemented and verified among Juniper and Cisco, and both of them. So both of these two are tested. I have absolutely, I don't have the overview over which ones have been implemented and tested as well. But the spec is open for anything can be done. That's kind of the point. Yes. But good question. Yes? Oh, sorry.
Hey, I'm Emil from KNet, and I'm also a student at TTU. And actually, one of the things that I'm looking into is protocol security and validating the protocols in a general sense. And that's why I wanted to ask if you are doing any kind of protocol verification in a formal sense for this, or if it's more practical testing.
So this specific option here has nothing to do with protocol, security, but it ensures that a MAC is calculated and ensure that nothing has been tampered with, including the TCP option header, a TCP header. And the problem with, for example, TLS and SSH and so on is that they all look at the payload. So you can reset any TLS session by injecting, something that looks to be valid with a reset bit set on it, and the session will just randomly drop. This is not about you can't tamper with the data since it's, basically, checked on validated. But it's not about did the person send what you really thought it would, and we have other protocol works that is both deployed as well as in the works on how do we ensure that, for example, the EAS, which is in the BGP the route that's in the BGP protocol, was actually advertised by the person who was supposed to, and so on. The work that's there has been ongoing for 15, 20 years, I think, for real. And it's a cost benefit right now in that it's super expensive to do it right. Everything needs to be signed. It's really cheap to do it as done today, and nobody is really willing to pay the full price, and therefore the lever right now goes here. So there are some prefix validation which is done internally in BGP, where you basically get a data feed from a server, a route server, that tells you this is the ones that are valid, and then you will either drop them if you think that yours is not enough. But if you have further questions like this, I would love to talk about it, maybe tonight or afterwards.
Okay. Any other questions?
Henrik Kamselund from Security. is it handled by the control plane, and what happens if you get like 1 million of these packets per second?
It is control plane handled. Yes, we're aware of that. If you get 1 million packets, usually your host path, the DOS protection should kick in. One thing is that we kind of can take most part, vendors, maybe not 1 million, but very close to. In fact, BDP tend to be like 99% of the control traffic in the first place, right? So we today sometimes from some platforms have had the problem with that we would outrun the DOS protection that have been put in place from the platforms because they assumed that we would never reach that amount of data. But if we have tens or hundreds of internet feed, or let's say tens of internet feeds, and then suddenly the system is restarting. You do a clear all and all of that. The amount of TCP/BDP data that comes in and out there is very big. Lots of messages, but not 1 million. Usually DDoS should take care of it. I'm sorry, I have one question though. Did anybody think that they were going to go home and take a look at this? We didn't do that before? Okay, sorry. I had hope. Oh, there was one. Okay, you saved my day. Thank you so much. Appreciate it. Thank you.